All right, so I'm going to go ahead and get science class started for today, and hopefully be a little more clear and less distracted than I was yesterday. So I'm going to attempt to talk about and discuss atoms, the periodic table, and then get into some real basic stuff about bonds when it comes to some real basic chemistry. So I'm going to do some various screen shares, and I'm going to avoid my PowerPoint for the day and just kind of pull up some different things. So I'm going to start with looking at just kind of our copy from the book. Let's talk about some real basic things first, and then we'll look at some different diagrams and try to get into some stuff in a little more detail later on. But initially, just to recap kind of what we talked about yesterday, atoms are essentially the smallest unit of matter that can be broken down, right? So essentially an atom you cannot break apart. It's the smallest possible form of matter that we have. And those atoms are essentially made up of a dense nucleus that houses the protons and the neutrons, and then electrons that orbit around the outside. So I'll pull up a diagram for that here in a little bit, but I want to kind of go down to kind of this middle section here and talk about this, because this is something I kind of skipped over yesterday. Earlier in the week, I talked about states of matter, solid, liquid, gas, etc. But today I want to talk about these different types of matter in terms of ways matter can be classified. So we've got elements, compounds, and mixtures, and so I want to first describe those. Elements are substances that cannot be broken down into any other substance, right? So everything that's on the periodic table, those are considered elements because you can break them down to a single atom of that element. So whether that is gold, iron, hydrogen, I'm not going to read the whole list, right? But those things, those are considered elements. Anything that can be broken down into a single atom of that substance, okay? Moving on down the list. Next, we have compounds. Compounds are substances formed of two or more elements that are chemically combined. In other words, they are bonded together to form a single atomic structure, or they won't come apart. So think of water, right? Water is made up of two atoms of hydrogen and one atom of oxygen, and those hydrogen and oxygen atoms are bonded together to form one molecule of water. So it isn't like you can pull apart the hydrogen and the oxygen from that molecule of water. They're bonded together to form a new compound. So again, compounds are substances formed of two or more elements, chemically combined in a definite proportion. So in other words, water is always two hydrogens and one oxygen. And you can see the little picture of a water molecule down here, and we're going to talk about bonds a little bit later on. Compounds also have properties that differ from the properties of the elements they contain. So think about water, right? Water is made up of hydrogen and oxygen, but on its own, hydrogen and oxygen don't resemble water in terms of the physical makeup, right? Hydrogen and oxygen typically exist in gas form, and we know water typically exists in liquid form. So when they combine together, they undergo a physical change, right? So that's common of compounds. So compounds are also represented by chemical formulas. So whereas when we get into talking about elements and their symbols represented on the periodic table, right? Compounds have unique chemical formulas that are written with those symbols in mind. So think about water, right? We know water is H2O, that you can see down here, and that is the chemical formula for water, 2 hydrogen to 1 oxygen. Right? And then lastly, here on this list, we have mixtures. And mixtures are physical combinations of two or more substances that keep their own properties, right? So for example, salt water is a mixture. Salt and water aren't mixed or aren't combined together through anything other than they're not bonded together, is I guess what I'm trying to say. Right? So the salt and the water exist together, but they're only mixed together, right? And so they will not, they're not actually chemically combined the way, say, like a water molecule. Or another way to think of it is maybe like a can of soda pop, right? There are lots of ingredients that go into that soda, right? So there's sugar, there might be caffeine, there might be carbon dioxide, there might be water. All those different things are mixed together to create soda, or pop, or whatever, however you want to call it, right? But they're not actually chemically combined, right? They're just mixed together. So that would be an example of a mixture. Okay? So before we kind of get into this last section about bonds, I want to pull up a couple different pictures. So bear with me while I kind of stop this and share new screens. So first, let's just take a look at the periodic table. Okay, so hopefully you can see this. All right, so I don't want to kind of spend too much time talking on the periodic table because you can really get lost in it. But essentially, the periodic table organizes all the known elements that we have, that we have discovered. The periodic table takes them and organizes them, right? So you notice all the different color coding, and you also notice that they're numbered in order, like 1, 2, 3, 4, 5, 6, and so on and so on. Okay, so first of all, just kind of keep in mind that all of the vertical columns, right, all of the elements in those columns tend to act similarly to one another just based on where they are and how they're ordered in the periodic table. And that has to do with their electrons and their, what we would call their valence electrons or their outermost electrons. If you don't know what the heck I'm talking about, that's okay, right? But essentially, elements react and gravitate to other elements based on kind of their electron rings, and that is a topic for another day. But bottom line is, if you can remember that all of the elements that are aligned in the same column act a certain way, and also all of the elements in certain rows also have certain other similarities. Now, they might be different, but they are, of course, different, right? But they're going to have different similarities as well, okay? So just keep in mind that it's organized vertically and horizontally with a purpose in mind, right? It's very specific. Lastly, all of these different colors, they kind of help break down different groups that exist on the periodic table, okay? So over here, I'm going to start on the right. These are the noble gases, okay? There are gases that tend to not want to bond to other gases. They are happiest left alone, and they tend to stay that way. But they are gases, like at normal temperatures, okay? These are the halogens, and these are kind of some other non-metals. So carbon, nitrogen, oxygen, right? Some of these, carbon tends to exist in a solid form, in a gas form, right? So most of these are gases. All of them are non-metals, right? Then we get into kind of this middle section, and these are typically going to be all metals of some variety. So we have some post-transition metals, and kind of these are considered the transition metals. I'll explain those on another day, but I just kind of want to keep going through these. And then over here, we have the alkali metals, which are very reactive, and as opposed to the noble gases, which don't like to react with any other elements, the alkali metals are very reactive. In other words, they like to react with other elements, and so they act distinctly different. And again, these are all typically going to be metals. All right, so enough of that. If none of that made sense, bear with me. It's okay. I just wanted to get that out there. And if you have questions on it, you can always ask me about them later. But I want to look at what one of those little squares looks like. So here's oxygen, okay? So I took oxygen, actually, come back to oxygen. Sorry. Okay, so here is a breakdown of carbon. So here is carbon square off of the periodic table. So first, I just want to go over what all these different things are that pop up on the periodic table. So this number, this is called the atomic number. So this is that number that they're all in order. So 1, 2, 3, 4, 5, 6, 7, and so on and so forth. That atomic number is equal to the number of protons in the nucleus. So there is always 6 protons in the nucleus of a carbon atom, okay? As well as the number of electrons in the electron cloud. Okay, so just remember, protons and electrons are always equal to each other because of that positive-negative balance. All right, so the atomic number tells you how many protons there are, how many electrons there are in a typical normal atom of, in this case, carbon, right? But that applies to all the elements, okay? This is the atomic symbol, right? So it's usually 1 or 2 letters, and it's just kind of an abbreviation, right? So when you see carbon in a chemical compound, you'll just see the letter C, and that's what it stands for. Then you'll obviously have its full name, and then down at the very bottom, you'll usually see a number like this, and the numbers get bigger the further you go down the periodic table, and that is the atomic mass. And the fancy definition for that would be the weighted average of the masses of all of the elements' isotopes. In other words, if you took the protons, the neutrons, the electrons, added them all together, they would come out to a mass of this, right? And so where this is useful is you can actually use the atomic mass to figure out how many neutrons a certain atom of a certain element might have, right? Because again, this atomic number up here tells us the amount of protons and the amount of electrons, but if we want to know neutrons, it isn't always the same. Now, in this case with carbon, it is, but that isn't the case with every element. In fact, most elements have a different number of neutrons than they do protons or electrons. How you would find that is you would round this number to the nearest whole number, right? So 12, subtract the atomic number from it, that would give you the number of neutrons that make up that element, right? So if there are 6 protons in an atom of carbon, 12 minus 6 would be 6, and there would be 6 neutrons in that one atom of carbon, okay? So the further you go down the periodic table, the more out of balance protons and neutrons tend to get, which means they act a little bit differently because the nucleus of those atoms becomes progressively more positively charged as opposed to. Okay. So, too much explanation. I don't have any live students, so I'm really left to my own devices to just ramble on. So if you're watching this video on YouTube, I apologize for being more boring than normal. All right. But anyway, I'm going to just keep powering through, and we'll see kind of where we end up. But I want to now look at so a couple different things. So first, this is oxygen. So we talked about the squares and kind of all the different pieces. So with oxygen, same thing. Atomic number is 8. That represents the number of protons and electrons. The chemical symbol, the element's name, and the atomic mass. So oxygen, again, similar to carbon, 16 minus 8. Oxygen also has 8 neutrons. So the reason that this is all helpful is we can begin to take that information and look and see what these elements actually look like, kind of a graphic model. And so what I'm talking about is before I confuse you too much. Okay, so this is oxygen also. Okay, so hopefully you can see this, okay? This is a diagram of what one atom of oxygen would look like. Obviously, just kind of basic. This is obviously more complicated than this, but I just wanted to show you to kind of give you an idea of a few things. So first of all, here's our nucleus, right? This is where the 8 protons and the 8 neutrons exist. And then again, we have electrons orbiting around the outside like we talked about. But without getting too in detail, electrons tend to organize themselves into these rings, okay? And the innermost ring of any atom can only fit 2 electrons. So these 2 electrons orbit in a kind of tighter circle, and then this outer layer can fit up to 8 electrons, but oxygen only has 8 total, so 2 are here, and 6, 1, 2, 3, 4, 5, 6. 6 are out here, okay? Now, without trying to confuse you too much, that outer ring of electrons is always kind of what is going to dictate or tell you how a certain element interacts with another element, because inevitably atoms of any element always are wanting to fill their outer electron rings. Okay? And so when we get into talking about bonds, the reason certain elements bond together is because atoms naturally want to gravitate to other atoms that help fill this ring. So oxygen, for example, has 1, 2, 3, 4, 5, 6 electrons in its outer ring, but it can fit 8. In other words, it wants 2 more, okay? So the reason water is such a strong bond, in other words, you can't break a water molecule apart, is because hydrogen and oxygen are natural partners when it comes to bonds. And so if we think about, and let me kind of move on and show you something slightly different. Sorry for all my jumping around. I'm trying to jump around as little as possible. But if we go back to this, so this is kind of where we left off with the lesson here. If we go down and we look at this picture in the bottom here, where it says covalent bond, ionic bond. First, let's just look at this right here. Ignore the covalent ionic. I'm going to describe that in a second. But let's just look at this bond. This is actually water, H2O. And notice this picture of water, or of the oxygen molecule, or the oxygen atom, I'm sorry, looks similar to the picture I just had up, right? So oxygen has its 1, 2 electrons orbiting around this middle ring. And in this outside ring, remember, oxygen only has 6 electrons. But because hydrogen has only 1 electron, hydrogen is our smallest element, right? It only has 1 electron and 1 proton. Okay? Hydrogen has 1 electron, and this other hydrogen also has only 1 electron. So together, those 2 atoms of hydrogen are sharing their electrons with water, right? And or with oxygen, sorry, right? To create a molecule of water. And if you notice, because hydrogen is sharing their electrons with oxygen, if you look at oxygen, it has now, after this bond, 1, 2, 3, 4, 5, 6, 7, 8. So its outer layer of electrons is now filled. And remember, the inner layer, or the first ring of electrons, can only fit 2. And so hydrogen, which only has 1, now, because it's sharing electrons with oxygen, now hydrogen has 1, 2. This hydrogen also has 1, 2. So its rings are filled up with electrons. And so when you have bonds with elements that have their outer rings filled, that you're going to have a very stable bond. So without going into too much more detail, let's just talk about what bonds are in general, okay? So when elements combine to form molecules, so down here we have water, and down here we have salt, or sodium chloride, right? So those are 2 examples of bonds. right? The bonds are the actual holding together of the two elements, or the multiple elements, right? And so there are two types, covalent and ionic. So with covalent bonds, atoms share electrons. In other words, like we talked about here, hydrogen and oxygen are sharing each other's electrons. And so in a covalent bond, you have a much more balanced and stronger connection, right? So because they're sharing electrons, they tend to be more stable and harder to break apart. They're a stronger bond. Ionic bonds come when atoms gain or lose electrons to become ions, or to become ionic, right? And that attraction between positively and negatively charged ions is what holds them together. So they're a much more volatile and weaker bond. They're easier to break apart. But basically, the way to remember it is ionic bonds take or give away electrons from one to the other, and covalent bonds are shared. Right? So notice here, with salt, or sodium chloride, over here, sodium, which only has one electron in its outer ring, it actually gives away its outer electron to chlorine, and chlorine gains an electron. And so they're kind of held together almost like magnetically, right? So that bond is much weaker and is easier to break. Okay, so that was a mouthful. All right, I'm sorry again if none of that made sense, but we'll just kind of keep on going. So I want to spend the last couple minutes just looking at a practice question. So I'm going to zoom out a little bit. Hopefully that's not too far to zoom out. Seems like it might be. Come on. Okay, so let's go with that. So we're just going to do number one, and I'll kind of walk everyone through it. So number one has to do with sodium chloride, right, or the ionic bond we just talked about. And it says sodium is represented by the chemical symbol Na, and chlorine is represented by the chemical symbol Cl. According to the text and the diagram on page 542, so the page we were just on talking about, you can kind of see the bottom of. What happens when sodium chloride forms? All right, so let's read through these options. And remember, sodium chloride is an ionic bond, meaning it is not sharing electrons like a covalent bond, but giving away or taking electrons. Okay, so A says the sodium atom loses an electron, becoming positively charged, and the chlorine atom gains an electron, becoming negatively charged. B, the sodium atom gains an electron, becoming negatively charged, and the chlorine atom loses an electron, becoming positive. C, the chlorine atom gains an electron, becoming positively charged, and the chlorine atom loses an electron, becoming negatively charged. Or D, sodium and chlorine atoms share a pair of electrons, becoming ions and forming a covalent bond. All right, so wow, that was a lot, and they're all obviously, A, B, and C are very similar, just kind of switching the wording around to try to be tricky, right? So the one thing that stands out is D is definitely the wrong. First of all, when atoms share electrons, they do not become ions, right? Ions are present in ionic bonds. So sodium and chlorine are not sharing electrons or forming a covalent bond. So D is kind of the first one I'd throw out. And just as a side note, with all of this positive and negative charge thing, remember yesterday when we talked about kind of the makeup of an atom? Protons, which exist in the nucleus of an atom, are positively charged, and electrons, the ones that are orbiting around, those are always negatively charged, okay? So in a normal atom of a normal element, there are always equal parts proton and electron is neutral, right? But in an ionic bond, because one atom is losing an electron and one is gaining it, that means that one atom, in this case, sodium, is losing an electron. So it actually has more protons than electrons, and because protons are positively charged, that sodium now becomes a positively charged ion. So notice the little plus here. That means sodium is going to be positively charged. Over here, chlorine is gaining an extra electron. That means they have more electrons than protons. They have more negative charges than positive charges. Okay? So the chlorine ion is going to be the negatively charged ion. And together they balance out to come together to form salt. Okay? So after that long-winded description, let's see which one of these A, B, or C matches up with that. A, the sodium atom loses an electron. So up here, that looks right. Sodium is losing the electron. Chlorine is gaining the electron, becoming positively charged. So sodium is becoming positively charged. That's right. And the chlorine atom gains an electron, becoming negatively charged. Okay. So without going any further, it looks like A is going to be the right one, right? Sodium is losing an electron, becomes now more positively charged. Chlorine is gaining an electron and becoming more negative. Okay, so with that, we're going to stop for the day. So if you have questions on this video, please email me, email us, contact us through the website. Come to class next time and you can ask questions either through the chat or on discussion. And with that, I will end class for the day. I hope everyone has a good weekend, and I will see you again Monday with some more science class in the afternoon. All right. Have a good weekend, everyone.